All right, as Jerry Reed sang in the title song to Smokey and the Bandit, we've got a long way to go and a short time to get there. Y'all know the movie. Y'all know the song. Good. All right. Not really. Okay. I want to be able to finish the notes today so that you have all of tomorrow and Monday to work on the final exam review. So I'll go kind of fast today. More faster than normal. More faster. Tuesday. he was better in the front row, I admit. But that took planning. You had to charge your iPad the night before to do that. All right, so here we go. In a box, right? In a box. We have a theorem here, and it's kind of related to a theorem we had earlier with differentiability. This theorem is the continuity implies integrability theorem. And all that means is if you have a function that is continuous, it is going to be integrable, meaning you're going to be able to find the antiderivative of it. You're going to be able to evaluate. You're going to be able to find the areas bounded by the curves. Of course, the contrapositive of that is negating the inverse. That means if it's not integrable, then it's not continuous. So if you have a continuous function, it is integrable. The one we had earlier in the year was very similar. It was this. It said D implies C. If a function is differentiable, if the derivative exists, then it's continuous. And that gave us a nice little contrapositive, gave us a whole category of functions that weren't differentiable. If they weren't continuous, they weren't differentiable. So now we can actually combine D implies C and C implies I. We can actually say if a function is differentiable, then it is integrable. That's the transitive property. And if it ain't integrable, then it ain't differentiable, y'all. Okay, here in the South, we don't allow it to be differentiated if you can't integrate it. All right? So, notice what the theorem does not say. The theorem does not say that if it's not continuous, it is not integrable. It doesn't say that. So there are some functions that are not continuous, and yet you can still find the area of the curve, under the curve. Por ejemplo, zum Beispiel, here's an example, 9. Evaluate the definite integral from -2 to 3 of our favorite new parent function, Señor Salta, right? By graphing it and finding the areas, using the areas to help us find the integral. So remember, the integral is really the net accumulation. Step 1, sketch the graph. So there is what it looks like. It's at 1, and then it's -1 to the left. We're only integrating, though, from -2 to 3. So what I can do then to find the actual areas instead of the approximation is just find the area of the two rectangles. Now, even though there is a discontinuity at 0, we can still say that the area is approaching the actual area if we had that hole plugged in. It's not like the area is escaping out and we have infinite area. It's still bounded by the y-axis and the curve where they intersect. Same thing up above here. Even though there's an open circle on the y-axis, the area is bounded by that graph as if it were a solid point. So we will be able to find the area. So let's go ahead and find the areas in the graph. We'll write them in there and we'll show them in our calculation. That's how we justify. So the area of the first one, let's see, it is 2 wide by 1 tall. So 2, yeah, 2. I got to catch up with you. The next one is 3 wide by 1 tall, which is 3. So those are the areas. Now we're going to use the areas to help us evaluate the integral. The integral from -2 to 3 of the absolute value of x over x with respect to x is, from left to right, what kind of 2 do we have? It's negative. Good, because we're integrating from left to right. And then what kind of 3 do we have? Positive, yeah. And so if you simplify that, you get 1. The net accumulation is 1. We lost 2, then we gained 3 back. We're 1 ahead at this point. That's what the definite integral always gives you, net accumulation. The area of that region is what? 5, right. So you wouldn't want to go to the paint store and order enough to cover 1 square foot of surface because you're going to come up 4 square feet short. I would recommend if you were going to paint it, not even to get enough to cover 5. Get enough to cover 10 because you always want to put 2 coats on. That's a life tip, right? Life hack. If you get the bare premium stuff, that's a primer and a final coat in one, then, yeah, I guess. Does that actually work? You're paying like $80 a gallon instead of like 13, so, yeah. Yeah. I guess if money is no object and you're lazy, get the one-step painting. Okay, cool. That's actually another life hack. Get rich, and then the life is easier for you because you can pay people to do things. All right. Math is a prerequisite, by the way, or not a prerequisite, but it's a good thing to have to help you along that road to riches. Calculus, right? Okay. Now this is by the way finding the area of holes or jumps. It's going to be easy to do every time. Holes and jumps do not limit your ability to find area. Later on in the year, though, we're going to have graphs like 1 over x, which have vertical asymptotes and horizontal asymptotes. Asymptotes are a little bit different. We're going to be looking for areas like from here going out to the right, and we're going to be looking at areas from there going towards the vertical asymptote. Those are called improper integrals. So vertical asymptotes aren't as surefire as holes and jumps. Sometimes, even though it's an unbounded region, it might be a finite area, and sometimes it's an unbounded region that's an infinite area. You'll have to wait for that, though. That's pretty exciting. So vertical asymptotes and horizontal asymptotes, a little bit harder to find areas of, but for holes and jumps, it's always a possibility. Okay, so here we go, example 10. We're going to look at a couple of examples where we have functions represented by tables or data charts. You're typically going to be asked to approximate a definite integral using one of those 4 methods that we know, right? Riemann sums with left, right, or midpoint, or trapezoidal methods. So let's go ahead and read. It says f is a continuous function. So now that we know it's continuous, we know it's whatable? Integrable. We know it's integrable, right? If it's continuous, it's not differentiable necessarily. It could be continuous and not differentiable. But if it's continuous, we know it is integrable. That's a hard word. So we know we're going to be able to find the antiderivative of it. It also says that the y values are greater than or equal to 0 for all x. Selected choice cut values are given in the table above. Nice. So we have values from 0 all the way to 3 at different intervals. It says to approximate the definite integral from 0 to 3 using the numeric methods. So that's not what it would say in an actual question. You'd be asked to use one of the methods. It'll say approximate this using a trapezoidal method indicated by the data, or a left Riemann approximation indicated by the data. But I'm going to do all of them so that you're ready for any one of them. The first thing you want to do when you're given a table of values and you have to find the integral by doing the numeric approximations is you have to look at the delta x, because we don't have an equation. We can't necessarily let delta x be what we want. We're at the mercy of the values that are given. So when it says as indicated by the data, that just means to use as many data points as possible. If we're going from 0 to 3, though, the first thing you might want to do is make sure that you're using the right data points. Sometimes they might give you extra information, like they'll have 2 more columns at 3.5 and 4, and you wouldn't want to use them. But in this case, we're using all of the columns. So now you want to find the delta x from one to the next. So from 0 to 0.5 is a half. Yeah, from 0.5 to 1 is another half. Okay, so it must be a half all the way through, right? Not necessarily. You got to check. 0.5, that's another 0.5, that's another 0.5, and then we got another 0.5. So lucky us, delta x, we could say, is 1/2. It's a uniform all the way through the table. That's nice. Because remember, if delta x is uniform, we can actually factor it out and expedite the process. So let's go ahead and say the integral from 0 to 3 of f of x dx is approximated by, and we'll just do part A. We'll use the left endpoint. Now, how many, bless you, how many intervals are we going to use here? Say, what's here? 7? Well, how many delta x did we calculate? 1, 2, 3, 4, 5, 6. That's another good reason to calculate delta x, is it tells you how many intervals you're going to have. We have 6 delta x's, so we're going to have 6 intervals. So we'll say L sub 6 equals. Now, because delta x is uniform, 1/2, we could factor it out. And then remember, just like we did when we were generating our y values ourselves by plugging them in, we're just going to add up then the first 6 y values. There's 7 data points. So it's going to be 2 plus 4 plus 6 plus 7 plus 4 plus 1. Stop before you write down the 5. So what do? We left justified the y values. If you want to distribute the 1/2 back through, it's a half times 2 plus a half times 4 plus a half times 6. That would be your width times the y value at the left endpoint. So when you have a table of values, it's actually a lot faster. It's real easy to do the numeric methods. If you want to start combining things as you write them down, like, I know it's going to be 2 plus 4, that's 7, minus 1, 6. You want to write a 6 right there? No, you do not, because then you're going to lose points. You're not indicating your method. So if you want to get a 2-for-1 deal, the values that are in the table need to show up in your calculation. And then the reward for that is you could stop there on a free response. It's a numeric answer. Okay? Is anyone curious what that actually equals? Not me, but y'all? It's the whole thing comes out to 12? Oh, nice. Good. Sweet. All right. So then we could also say that the integral is squiggled by r sub 6, which equals 1/2 uniform delta x. Now we're going to skip the first y value, and we're going to right justify the 6 value. So starting with 4. So 4 plus 6 plus 7 plus 4 plus 1 plus 5. Yeah. Some people actually like to start at the back end and go 5 plus 1 plus 4 plus 7. That's fine if your delta x is uniform, not necessarily as wide if it's or wise if it's not. So there's the left and right. That's pretty easy. Can we do a midpoint here? Not with 6 intervals, right? Because to do that, I would need to know the y value at 0.25. Do we have that? No. But there is a way that you can do a midpoint. Yeah, you just have to do it on 3 intervals instead of 6. So now you got to be careful. Now if you're skipping every other interval, you're going from 0 to 1. Your delta x is 1. You're going from 1 to 2. Your delta x is 1. So now you would factor the delta x out, which is 1, and now you're adding up the midpoint value. So between 0 and 1, halfway is a half. Its y value is 4. Halfway between 1 and 2 is 1.5. Its y value is 7. And halfway between 2 and 3 is 2.5. Its y value is 1. So that'll be 4 plus 7 plus 1. So maybe that's not the best practice because you're actually using fewer values. And in general, the more values you use, the more accurate it is. But certainly it works in theory. And I have seen them ask midpoint from data. You actually don't need it to be uniform all the way across. All you need is consecutive intervals to be the same. So like 0.5, 0.5. And then the next two could be 0.3, 0.3. As long as you have consecutive intervals that are the same width, you can skip every other one and do a midpoint. Delta x? Method? Yeah. Yeah, see how I showed the one up at the top? Yeah, and you have to have the one out front. Yeah, that's a good point, because one is the identity element of multiplication. You might say, I don't need it, but if you want it to count for your method, you do need it. The other way to get around doing that, if you just want to do all the math in your head, you would say m of 3 equals delta x times, and then you'd have to say f of 0.5 plus, and then you don't want to do that, right? Because then you're going to have to come back and plug in. But that's another way to indicate your method, and then feel free to write down the numeric answer. But this is the 2-for-1 method, indicating your method and your answer all in one. All right, so now back to the trapezoidal method. We'll call this D. We can go back to 6 again. So that'll be T sub 6, which equals. So remember, for the trapezoid, the pattern is 1/2 is always out front because it's part of the trapezoidal area formula. Delta x, when it's uniform, can come out front. It's also 1/2, right? Okay, now I put the brackets there. You're using all the y values. So if you have 6 subintervals, you're actually going to have 7 terms. You're going to double all the guys in the middle there, and then the last guys, or the first and last guys, 2 and 5, are single. So indicating your method, here's what we'll do. We'll do 2 plus, and then 2 times 4. Not 8, but 2 times 4. The next one will be not 12, but 2 times 6. The next one, not 14, but 2 times 7, so on and so forth, plus 2 times 4, plus 2 times 1. And then finally, plus 5. And I got it in there, barely. That indicates your method. We see that you're doubling all the values from the table. That's the 2 for 1. Indicates your method and it's numeric. Remember that this is also the average of which two? The left and right. So if you had already done the left and right, I doubt that would ever happen on a free response. But if they had you do left, then the right, then the trapezoidal, you could also say this, L of 6. The integral is squiggled by, let me back up here. You could say the integral is approximated by T sub 6, which equals L sub 6 plus R sub 6 over 2. And then you could just take your answer, assuming they were simplified, right? 12 and plus whatever divided by 2. I don't think you'd want to write all of that unsimplified plus all of that unsimplified divided by 2. But it would come out to be the same as the trapezoidal formula down here. Okay, the follow-up question here says, could any of these integral approximations actually represent the area of the region bounded by the graph of f of x, the x-axis from 0 to 3? When is the definite integral going to give you the area every time? It's only on one condition. When you're integrating from left to right over with non-negative values. All of the y values in the chart that were given to us are certainly positive, but what about all the ones in between the values that we don't have? Because it is continuous. We don't know? Yeah, I was wondering why that was there. It says, hey, even the y values you can't see, they're still going to be non-negative. So the answer to this question is yes. Exclamation point. A little enthusiasm in your answer. Yes. All can. Right? They all can represent possible approximations of the area of the region. Okay. I take that back. There's another time the definite integral will give you the area, right? When you're integrating from right to left and your region is negative. That's the other time too. Yeah. Okay, sweet. And then the last part here is just a review. Okay, approximate f prime of 1. If you're ever given a free response with data, they'll have you do the numeric approximations, and they typically have you approximate a derivative. So remember, anytime they say approximate or estimate, you're on squiggle alert. So to approximate the slope at 1, you check to see if 1 is in the table, and it is. And then you check the spacing on either side. And in this case, it's equal spacing on either side. So here you could say f prime of 1 squiggles, and you really have three options. You could use the point of interest on the one to the left. So you could say 6 minus 4 over 1 minus 0.5. That would be using 0.5 and 1. Or you could say it's approximated by 1 and 1.5, which would be 7 minus 6 over 1.5 minus 1. Or you can even use the 2 on either side, namely the 0.5 and the 1.5. So that could be 7 minus 4 all over 1.5 minus 0.5. And again, when you show the difference quotient with numbers, it's a 2 for 1 deal again. You're indicating your method, and it's a numeric answer. So fight the urge on a free response then to do too much in your head, right? 7 minus 4 is 3 on that last one. But if you don't show a difference quotient with numbers from the table, you're not going to get credit. So any one of those would get credit. The common error that students want to make here is, again, because your table is written as a row of x's over a rows of y's, it's really easy to do change in x divided by change in y instead of change in y over change in x. So be very, very careful. You would still get 1 out of 2. If you showed a difference quotient but it was the wrong one, you'd get credit for a difference quotient but not for the answer. So good to know. All right, any comments or questions on that one? Uniform delta x. Still can factor it out, expedite the process. All right, example 11. Hey, more data. Like Christmas 2 days in a row. F is continuous for all given x. Here are choice cuts. Sweet. So now we're looking at the integral on part A from 1 to 8. Are we going to use all the data in the table table? No. We're starting at 1, so nice try, College Board, tempting me with another column. And now we use all the rest of them, right? No. They tempted us twice, 1 on each end. So that's the first thing you want to get straight. We're going to use those data points. All right, so now since I'm at the mercy of the data, let's compute our delta x's, which will also help us indicate our method numerically and tell us how many subintervals we can use. From 1 to 3, it's 2. So it must be 2 all the way through, yeah? Yeah, right? That's shallow thinking. From 3 to 6, that's 3. Oh, okay. So they're getting bigger by 1 every time. So the next one must be 4. No, that's not how things work. It's 0.6. Actually do the math. And then from 6.6 to 8, that is also known as a width of 1.4. Okay, so do we have a uniform delta x? No. Are we going to be able to factor it out? Sadly not. But we could still go width times height plus width times height plus width times height. It's going to be just as easy, just a little bit more writing. So here we go. You would write, if they ask you for any one of them, you would say the integral from 1 to 8 of f of x dx squiggles. Let's keep the order the same. We'll say A. Let's do L sub, how many intervals did we have? How many delta x's did we calculate? 4, right? So we'll go L sub 4, which equals. All right, so now the first width is 2. And which y value are we going to use? The 3 on the left or the 3 on the right? The 3 on the left, right? We're left justifying it. Good. Plus the next width of 3 times which y value? The 3 on the left or the 1 on the right? 3 on the left. Yeah, so we're still left justifying it. We're just associating each one with the width. The next width is 0.6, and we're going to multiply that by the number that's to the left of it, which is 1, and then plus the last width of 1.4 times the width to its left, which is 5. So we still use 3315 and not the 8. We just associated them with different widths. And that's your 2 for 1 right there. Every number that's in that calculation is in the table, either given to us or you calculated with your widths. All right, let's do the next one. Letter B, R sub 4. Our first width is 2. Now the y value is going to be the 3 on the left or the 3 on the right? 3 on the right. Good. Plus the 3 now times the what? 1 on the right plus 0.6 times the 5 on the right plus 1.4 times the 8 on the right. So we skipped the first 3. We did 3, 1, 5, 8. There you go. Not that bad. So don't ever assume that your delta x is uniform from data. Actually calculate it. Are we going to be able to pull off a midpoint here? The only way with data is to skip an interval. So if I went from 1 to 6, what's the midpoint from 1 to 6? The midpoint of any two numbers is their average. 1 plus 6 is 7. Half of 7 is 3.5. Do we have the y value at 3.5? No, we have it at 3. So we could do like some kind of like in-between interval thing, but we can't do a true midpoint. So you wouldn't be asked to do the midpoint for something like this. But certainly we could do the trapezoidal. So let's talk about the trapezoidal pattern. The number you can always pull out for the trapezoidal is the 1/2, because that's part of the formula for the trapezoid. But unfortunately, our delta x is not uniform. So I can't pull it out, which means I can't do the old pattern of add them all up and double the ones in the middle. I actually have to do separate calculations, because the values in the middle are going to be associated one each with different widths. So here's what we'll do. We'll do the first width of 2 times the sum of the two values flanking that width. 3 plus 3. You want to call it 6 or 3 plus 3? 3 plus 3. Good. Plus, we'll go to the next width of 3, and once again, you can draw your arrows like that. The two flanking the width you drew are 3 plus 1. Plus the next width of 0.6 times the sum, 1 plus 5, plus 1.4 times the sum of each side, 5 plus 8. So again, if you notice, you're still using the interior values twice. Here's that 3 used twice. Here's the 1 used twice. There's the 5 used twice. They're just associated one apiece with different widths. And the 1/2 is still out front. So that's the easy way to do the trapezoidal when the widths aren't the same. All right, part B. Could any of those approximations represent the areas of the regions bounded by the graph of f, the x-axis from 1 to 8? No. Again, all the y values we used are positive, but because we didn't get that little thing given, like f of x is greater than or equal to 0 for all x, we can't assume that they're positive. We can easily have negative numbers here. So could they necessarily? Yes, they could, but in general, no. We don't know if f takes on negative values from 1 to 8. Yeah. So they certainly could. It's possible, but in general, no. All right, and then it says approximate f prime of 7. So we're approximating the derivative again at a point. Is 7 in the table? No, so this is the case that they've been leaning toward here in recent years. F prime of 7. 7 is not in the table, but it would fall somewhere between 6.6 and 8. So now the way to calculate the slope of the tangent line approximation is to use the points on either side of where it would be. So that would be 8 minus 5, change in the y values, over 8 minus 6.6, the corresponding change in the x values. So again, make sure you do y's over x. You could do 5 minus 8 over 6.6 minus 8. That would work. But if you get in the habit of doing right minus left, then when you do particle motion problems, that's the displacement, which is a vector. So it's always good to get in that habit. Final minus initial. The bigger x value is y value minus the smaller x value is y value. All right, so there's your lesson on data or data tables. They are a favorite type of question among College Board, okay? But that's how you do the methods. It's a lot easier, actually. The values are already there. You don't have to partition it. You don't have to find your own delta x. Y values are just staring at you like toys on a shelf waiting to go home for Christmas. All right. Here's a summary of some of the important integral properties. We've been using some of these. First of all, if f of x is defined at some value, call it a, then what do you think the integral is from a to a of the function? Yeah, it should be 0. If we think of the definite integral as net accumulation from a to a, how much have we accumulated if we let no time go by? We have collected nothing, 0. If you want to think about it in terms of area, what's the width from a to a? 0, right? So either way, it's 0. If you haven't gone anywhere, you haven't done anything, right? But that's not what ships are designed for, to stay in the harbor. Okay, number 2. If f is integrable on the closed interval from a to b, then we saw this property. The integral from a to b is the opposite of the integral from b to a, which essentially means if you ever need to flip your interval of integration, that's okay. Just do what out front? Change the sign. Yeah. If you have a constant multiple, call him lil c, you can pull him out front, and then to evaluate the integral of that constant from a to b, you just multiply by the width. That one's kind of interesting. Let's see why. Okay, good. So if I graph y equals c, he'll look like a horizontal line. If I'm integrating from a to b, that just turns into the integral of a rectangle, which is going to be c units tall by b minus a units wide. So the area would be c times b minus a. So whether you want to remember that or you just want to like sketch the horizontal line and make sense of it graphically, that's fine. This is a pretty useful one that we've kind of been using. The integral of multiple terms is multiple terms with integrals in each of them. In other words, if you're trying to integrate a function that has multiple terms, you could take the integral of each term separately, just like with the derivative. Multiple terms turn into kind of their own separate little problem. If you have a constant multiple, c times some function, you're going to be able to pull that out front, integrate, and then multiply by c. This is the guy that I call the rider. And this is going to be very, very important when we get into integration by use substitution and pattern recognition. Any constant multiple that's there in the beginning, he'll be there in the end. And then we have that travel agent little identity here that says the integral from a to b is the integral from a to c plus then c to b. And it's important when you're adding them that the c's correspond like that. Because on the left, it's your final or it's your destination, and on the next term, it's your point of origin, okay? And you have to leave from where you are, right? You can't leave from where you're not, right? I'm going to fly to Dallas out of San Antonio. I'd love to fly to Dallas out of Dallas. Then I wouldn't need to fly, but I'm not in Dallas. See how that works? Okay. Let's use some of those properties to do example 12. If the integral from 0 to 10 of some function is 17. Oh, that's nice. Okay. I accumulated 17 things as I went from left to right from 0 to 10. And for the same function, if I go from 0 to 8, I've accumulated 12 things. That's nice too. We want to find, whoa boy, the integral from 8 to 10 of 3 f of x plus 2. This is another favorite type of question for multiple choice. Makes great multiple choice questions. Our goal here is to somehow write the integral that we're trying to evaluate in terms of the information that we're given. So this is why I call it the flight attendant problem. You go, not the flight attendant, I call it the travel agent problem. If you're already in the air, I don't need the flight attendant can do much for your course. But let's say that our goal is to fly from 8 to 10, right? That's what we need to do. You want to fly from 8 to 10. Well, you look at the flights available. We don't have direct flights from 8 to 10 or from 10 to 8. We have a flight that goes from 0 to 10 and back, 10 to 0. And we have a flight that goes from 0 to 8 and from 8 to 0. So you as the travel agent have to put together the itinerary for that person, right? So that's ultimately what we're going to have to do. We're going to have to use both of them. But it all starts with this right here. You're trying to isolate the f of x integrals so that you can use these two pieces of information. So using the properties above, I'll do it in baby steps here at first. We got the integral from 8 to 10 of 3f of x dx plus the integral from 8 to 10 of 2 dx, right? That's using this property here, property number 4. You got multiple terms. You can give them each their own integral. And this is where dx is important. If you technically leave off the dx, you're not always docked. But if you didn't have that highlighted dx right there, now you would get docked because what follows it would still be considered part of the integrand. So make sure you have them. And now this little fella right here, this little 3, he needs to come out front. He's the writer. So it's 3 integral from 8 to 10 of f of x dx plus, this guy is actually ready to be evaluated. But I'm going to go ahead and evaluate it all at one time. All right, so now what I've done is I've at least isolated this part right here. And here's where the travel agent comes in. 3 beefy brackets. I want to start at 8, right? I've got to start at 8. So I'm going to write the integral as from 8 to something. All right, so we go check and we see what we have available. The only flight that involves 8 is one that goes from 8 to 0 or 0 to 8, right? We can always flip the interval. That's why I say from 0 to 8 or 8 to 0. So I'm going to have a connecting flight at 0, right? I'm going to have to do that. And then plus, well, not yet. Right now we don't even know about plus or minus. Right now we're just mapping the itinerary. We are just mapping our itinerary right now. I have to start at 8. There's only one option to fly to 0, okay? And now I'm at 0, right? So I got to start at 0, and then I can fly to 10. Okay, cool. I've always wanted to visit 0, so this is a nice way to do it, a connecting flight. And then, of course, plus the integral that's already there waiting to be integrated. Now, when you evaluate it, this is where you decide if it's going to be positive or negative based upon what was given. So let's go ahead and evaluate it. We got a 3 out front. The integral from 8 to 0 is what we want. Well, we have the integral from 0 to 8 being positive 12. So now the integral from 8 to 0 should be what? Negative 12. Good. So that's where you make it negative. Not in your itinerary. Your itinerary has to start where you want and end where you want. Plus, now the integral from 0 to 10. 0 to 10 was given. I don't have to do anything. It is 17. I don't have to flip it or anything. And then, of course, let's go ahead and integrate this guy to the second term that's been patiently waiting. Remember, that's the constant, so it's a horizontal line from 8 to 10. So it's going to be 2 units tall, because that's the integrand. And how wide is it from 8 to 10? I'll just put 10 minus 8, right, which is also 2 units wide. So now in the end, you could simplify, unless this was a free response, but it wouldn't be. So you get 17 minus 12 is 5 times 3 is 15 plus 4. You end up with 19. And you can imagine all kinds of other answer choices that arise from you forgetting to do any number of things. Make things negative when they should be positive. If you don't have this 3 with parentheses, it would only be multiplied by one of them, not both. Yes, sir, Colin.
So I've got a question. Given your information, you know that the integral from 0 to 10 of f of x dx is equal to the integral from 0 to 8 of f of x plus the integral from 8 to 10 of f of x dx. So you know that 17 equals 12 plus the integral from 8 to 10.
17 equals 12? Is that what you just said?
17 equals 12 plus the integral from 8 to 10 of f of x dx. So you know that the integral from 8 to 10 of f of x dx is equal to 5. Just from the information given, not even looking at the other part.
Okay.
So,
You think your clients would understand that if you were their travel agent?
sure.
Okay, good. Like I said, these are going to show up as what type of question? Probably a multiple choice, more than likely. Where the work doesn't matter. So if you think about this differently and you get the right answer, go for it. Go for it. Right. Absolutely. Don't let me mess you up with the way your brain is wired. If it were a free response, then you would still get credit as long as you write down the right numbers. Okay, and you don't just put the answer. Yeah, so that's fine. Everyone okay with that? You got a different way? I don't think that way. I would ask you, if I were your client, I'd say, can you repeat that, please? Slower. Can you write it down? Okay, all right. And then I'll trust you maybe, okay? All right, example 13. Kind of the same thing, kind of. We've got an integral from 4 to negative 6 given for the function f, an integral from 3 to 7, and an integral from 4 to 7. So we basically have 3 different flights that go both ways, 4 to 6, negative 6, and negative 6 to 4, 3 to 7, 7 to 3 if we need it, 4 to 7, 7 to 4 if we need it. We're trying to find the integral from negative 6 to 3 of f of x halves minus 3. So again, the systematic process is to try and isolate the integral of f of x. So you could probably do it in one step. The first term is going to have a 1/2 factor that you could bring out, negative 6 to 3 of f of x. Don't forget the dx. And then minus the integral from negative 6 to 3 of 3 dx. That's where you need to be to start. Now the last one, because it's a constant, we can evaluate it. This is what we need to work on. So if you want to do that however you want, if you can look at those 3 columns and know what that answer is, you can write it down on the next line. That would be fine. I don't think that way. I've got to map it out. So I'm going to start over here to the left. I got a 1/2. And this is going to be minus. If you want to go ahead and evaluate this one, you can. It's going to be 3 units tall by, from negative 6 to 3. Yeah, 9 units. So that's going to end up being a 27. Minus a 27. All right, so for me, I'm starting at negative 6. So I'm starting at negative 6. And let's see what we have at our option here. Well, negative 6 is, there's only one flight to take me to 4. So I'll fly to 4. All right, so now I'm at 4. So I'll pick up here at 4. And now I need to go where 4 takes me. Ultimately, I'm trying to get to 3. But there's only one other one that has a different route that doesn't take me right back where I started. And 4 takes me to 7. So I'll fly from 4 to 7. I have 2 connecting flights in this one. Wow, okay, so I'll get 2 T-shirts in the airport to say I was there. And then I pick up at 7, and please let there be a flight from 7 to where I want to end up. Oh, there is. Good for me. So I'll fly then from 7 to 3, and I'll be home for the holidays in no time. All right, so that's mapping out the itinerary, right? From negative 6 to 4, from 4 to 7, from 7 to 3. They're all added together. Now's the time where we decide if they're positive or negative. So from negative 6 to 4, we got from 4 to negative 6 was negative 3. So because I have to flip it, it's now what type of 3? Positive 3. So I'll drop in a positive 3 here. From 4 to 7. 4 to 7 was given as positive 5. Don't need to flip that one at all, so that's still plus 5. And then 7 to 3. Well, 3 to 7 is 9, so 7 to 3 should be negative 9. Right, negative 9. So that takes care of that one, and then, of course, we've already evaluated that one, so minus 27. So now you can go forward. It's negative 1/2 minus 27, which is negative 55 halves, or, of course, negative 27.5. Either one of those. Colin, did you know that was negative 1 in your head right away? Yeah. I'm just curious if it worked with. Okay. The other one was a little bit easier. Yeah, I agree. Yep. Okay, cool. All right, so they're kind of fun, right? Kind of fun. I kind of like these types. They're fun. You feel like you're helping people out, right? You get them where they need to go. If you like doing that for real, maybe a travel agent is in your future. Okay. What's that? Well, I know. There's still professional travel agents. Yeah. And they give you that personal touch that some people like. You don't like just like going to a website, right? That Trivago guy, kind of creepy anyway, right? Trivago. Hey, button your shirt, guy, right? All right, example 14. Example 14. Oh, that's the gnome, right? The little gnome. Okay. Yeah, he seems like he's a blast. Can you speak up? I didn't hear you. The integral from 0 to pi of sine of x is 2. That's a true fact. Use this fact and symmetry of the graph of sine of x to find the following. So we'll end with this today, hopefully before they come and bother us. All right, so here's the graph of Sahala, right? And from 0 to pi, they told us that the area of this whole region is 2. And you can't see that because it's also a dark color. 2, the area that's 2. Now, the nice thing about the sine and cosine is not only are the lobes symmetrical above and below the x-axis, but they also have lines of symmetry through their local max and mins, vertical lines of symmetry. So if the entire shaded region is 2, then what should each of the regions on either side of that line be? 1. Yeah, so instead of calling the whole thing 2, let's just call that one 1. And now it looks like one of those little creepy McDonald's things, right? Or maybe it's the mushroom from, yeah, it's maybe it looks like the mushrooms from Mario Brothers. Is that what you said? Super Mario Brothers? Or what'd you say? Yeah, kind of like the hamburger guy. Yeah, Robble. Or is that Grimace? I don't know. I know Burger King is the king. Snoopy. Mind your own business. All right. Here we go. The integral from pi to 2 pi of sine of x. That's what we want. The integral from pi to 2 pi of sine of x. Well, let's go ahead and extend this graph. It would be from there. So the integral from pi to 2 pi would be this region here. Guess what it's going to be? You mean 2? It should be negative 2, right? The magnitude of the region is 2. The area of the region is 2. But because we're going from left to right and it's below, it's negative 2. Good. What about the integral from 0 to 2 pi? That one should be 0. We gained 2 units going from 0 to pi, and we lost 2 units from pi to 2 pi. We're back where we started. The net accumulation is 0. Excellent. What about from pi to pi halves? Good. That's going from right to left, and it's above, so it's the opposite. It'll be negative 1, like y'all said. Good. All right, from 0 to pi of 2 plus sine of x. 2 pi plus 2? Okay, wait, hold on. I got to catch up with you. You could think of this 2 ways. You could think of it graphically. If you add 2 to sine, it raises the graph up 2 units, right? Making a platform, a rectangular platform that is 2 units wide by, in this case, pi units long. Or you could do the property that we just said. You can split it up by giving each one their own integral. So whichever way you do it, you'll get the same answer. This one then is going to be 2 units tall by pi minus 0 pi units wide. So it's 2 times pi. And then, of course, the integral from 0 to pi, we already said was 2. So the answer is 2 plus 2 pi, or 2 pi plus 2, as Colin said right away. All right, what about 2 times sine of x? Pull the 2 out front, right? It's a constant multiple. He goes along for the ride. So you can evaluate this, which we know is 2, times the 2 that's already there. Yeah, you get 4. Excellent, excellent, excellent. All right. What about sine of x minus 2? This one's a little bit more challenging. What does replacing x with x minus 2 do to every graph? Shifts it right 2 units. Right. So now we're at 2 and pi plus 2 to kind of be where we were before. So now I want the integral from 2 to pi plus 2. Well, it's the same exact region. It's just in a different spot. And since we've adjusted our intervals of integration, it's still 2. Yeah. So if it's a minus here, x minus 2, it moves to the right. So as long as you add 2 to your original intervals, 0 plus 2, pi plus 2, you're integrating the same region just in a different spot. So it is 2. This one here, this one's kind of interesting. What does replacing x with 1/2 x do? That's a horizontal, is it stretch or compression? Stretch, yeah, by a factor of 2. That's interesting, because then it's going to take the pi and stretch it all the way to 2 pi, and at pi we're going to have the high point. That graph is going to look like this. And now I want to know, what is this area? How do you know it's still 2? You think it's exactly the same? I just stretch it. It still has the same height as before. It's not like we're conserving mass or energy, right? Normally, if you have something and you pull it, it's going to lower the height. That's not how transformations work, though. It's still just as high. It can't be the same. It's got to be bigger. But how much bigger? Double? Did you measure it last night when I wasn't here? How'd you do that? I doubled the width, but how does that double the area? We better, I'm not comfortable just saying it's double the area. I'm not comfortable with that. I'm sorry. So here's what I'm going to do. I'm going to say, let u, the letter u, not you personally, be 1/2 x. Are you okay with that? The thing that was throwing me off was the fact that that was an x halves and not an x. So because I wish that were a single variable, I'm going to make it a single variable. So now that becomes sine of u. Sweet. The only problem now is if I have everything in terms of u's, then I got to convert everything that has an x or a dx into a u or a du. So how am I going to replace a dx with du? Well, let me take the derivative of this, both sides, in differential form. Remember that? The derivative of u is du. The derivative of 1/2 x is 1/2 dx. Remember doing that? Or you could do it, the derivative of u with respect to x is 1/2 and multiply both sides by an x. And that means then that dx is equal to, if I solve for it, 2 du. 2 du. Okay, so now I have my du. I'll put it at the back there. And I have this factor of 2 that's kind of residual. I'll put him out front because he's a factor. And now the last thing I have to do is these are actual x values from x equals 0 to x equals 2 pi. I need to turn those into u values. Well, that same equation that I boxed does the trick. When x is 0, what is u? That always bothers me when I say that. Yeah, u is 0, right? That'd be a bad redneck motivational speaker. U is 0. All right. When x is 2 pi, what is u? Pi. Okay. So here's what I've done. I have now rewritten the definite integral as the integral from 0 to pi of sine of u du. Just like when we had derivative of y with respect to t or derivative of y with respect to m, this u, du, and u just defines the variables. As long as these are the same, it could be anything. I can rewrite that as 2 times the integral from 0 to pi of sine of z dz, and it's the exact same thing. I could even call it the integral from 0 to pi of sine of x dx, which, hey, wait a minute, what was that equal to? That was equal to 2, right? That was what was given. Times the 2 that's out front. What did it in fact do to the area? It doubled it. Y'all were right. What we just did right here is a method that we're going to do again in section 4.4. It's called u substitution. And what it does is it replaces a composite function like x halves with a single letter, and then you change everything into that new letter in terms of u, and it makes the question a little bit easier to work with. All right? You could have used u substitution over here as well. You could have let u equal x minus 2. If you don't understand that right now, don't worry about it. That is your sneak preview of u substitution. All right, what about 8? The integral from negative pi to pi. All right, well, negative pi is over here. So that's going to end up being a negative 2. From 0 to pi is positive 2. Those should cancel out, right, giving you 0. What the heck? We got cosine in here. How'd he get in? Cosine. Okay, that's a different graph. Cosine looks like this. And we're going from 0 here to the halfway point, which is here, pi. So I want this plus that. What do you know about the cosine graph and the sine graph? They're shifted, right. They have the exact same lobes, just shifted. So this should be 1, and that should be 1, area-wise, yeah? But because I'm finding the integral and not the area, those should also cancel out, right? And that looks like a McDonald's cheeseburger sandwich if you ever open it right there, right? You open up the bun and you ever looked inside? There's like that color, red and yellow squished together with a little pickle on it. Speaking of McDonald's again. This doesn't remind you of mustard and ketchup mixed together? What's the answer here? It's 0. Yes?
So even if we didn't know the area, so we still figure out that was 0?
How?
Well, because with cosine, isn't it like perfectly?
Yeah, very good. Very good. You have an even, yes, you could. Yeah. It would be irregardless, or regardless, or irregardless, right? This would be, let's call this M, and let's call this M. We know because of the symmetry, they're the same. Whatever that number is, doesn't matter. They're opposites. They should cancel. Yeah, very good. Very good. It's 0. All right, what about from 0 to 2 pi of cosine? Yeah, that one, we get a 1 here, we get 2 there, and we get a 1 there. That still should cancel out and give you 0. All right, one more. What about the integral from negative pi 20 seconds to positive pi 20 seconds of sine of x with respect to x? Wait till I finish writing it. What did you say? Zorro? I like Batman better. Zorro. We're gonna learn a method later in the year called the backwards Zorro method. Did you say Zorro or 0? It's Zero. Okay. Here's why. Sine of x has what type of symmetry? I haven't heard it yet, but I hear an alarm. No. Sine of x has what type of symmetry? Origin symmetry is the right answer. That's rotational symmetry. If you ever integrate an origin symmetric function over a symmetrical interval, what should the net accumulation be? Should always be 0. Yeah. Should always be 0. When you integrate an odd function on a symmetrical interval, the integral from negative a to a of f of x dx is 0 if f of x is odd. And remember, the test for odd is f of negative x is the opposite of f of x. And that's why you get 0. Because it'll always cancel itself out from high to low, as long as it's a symmetrical interval. That's kind of a nice thing to take away here. Let's take away something else soon. Are you on that in the office? All right. Well, luckily we're done. So you like the sound of that alarm, you could just keep replaying this last little part over.